Well, thank you. Thank you very much for inviting me to describe our recent work on benchmarking robot manipulation policies. This work was done by my students Yash, Yidi, Kashu, and Chenyu. So there are yeah.
Actually, a little bit further away from the mic.
Okay, sure. Like here. Okay. So we see robot foundation models, and we saw many in this conference as well. And these are policies that are generalists, and they can achieve more and more tasks, right? They can attempt more and more tasks. And as the capability of our policies increases, their benchmarking becomes harder and harder. Because why benchmarking is harder? Well, first of all, in the real world, here's how we benchmark policies. And this comes from my own lab when we were trying to compute our real world results. You have your robot, and you have a specific task, and you initialize your scene, and then you deploy the policy, so you let the robot act. Then the robot sends the result, right? So you get the resulting scene, and then you need to evaluate. And guess who evaluates that? The student itself. The student who is an author in the paper will evaluate. And after the evaluation, which for sure is going to be subjective, whether your robot achieved the task or not, then you reset the scene. And you repeat this again and again. And if you want to do multiple seeds, you need to do the same reset multiple times for the same policy, and then you need to do the same thing for the baselines. And I would definitely not trust any human do these evaluations in the real world, let alone the authors that also have conflict of interest. So this seems very difficult. This benchmarking seems very difficult. Yeah, and as the task scales, this becomes even worse because you need to repeat this process for different tasks. Now, there are multiple benchmarks in simulation that I personally, for sure, my lab definitely uses because we think that this is a way to do apples-to-apples comparisons using the same data across different policy architectures, okay? And we thought that this is very important because we even now believe a lot on inductive biases in architectures, and we wanted to evaluate which one can generalize better with the same amount of data. So this is what these benchmarks are made to estimate, okay? RL Bench, Colosseum, Libero, Calvin, and they train and test in the same domain. This is the idea. You have your policy, you trained it on that data, you can pre-train it if you want, but eventually, because the domain is so narrow, pre-training may not matter that much, okay? And there are these robot benchmarks in the real world that I said are a little bit kind of silly in the era of foundation policies that defined, let's say, very few tasks like pouring, scooping, zipping, insertion, and they give you the assets to have apples-to-apples comparisons, and you need to repeat this resetting process that I showed you earlier. So this is also not very scalable. So we were very inspired by this work, LM Arena, Language Model Arena. What happens there is you have a human user that you don't even need to pay, and this human user submits a request, and then two language models are sampled, and you don't even know which language models are those. They generate two responses, and the human user needs to prefer one of the two responses. And then these preferences across users are aggregated, and then the result is a leaderboard of language models on how much human users like them and agree with them. And CEOs of many companies, when they wake up, they go and check that leaderboard because this really, really matters, right? And this leaderboard has really changed the arena of language models. So this seems to me like a fantastic way to benchmark. And notice that there is no notion of training data anymore. It's not like, oh, you're going to be trained, on the same training data, and then I'm going to evaluate you. No, everybody can train on whatever training data they want. So there is a simulation benchmark that we're very excited about. It's called Behavior, that tried to do something similar. They made a lot of nice simulated scenes. There is an enormous human effort here, by the way, just to make the scenes, the assets, the tasks, etc. And there are no training demonstrations, so you cannot train there. It's just for evaluation. And the truth is that, all policies get 0, so it has not been really used because policies just don't generalize there out of the box. And this is a big difference. This is a big difference between language models and robot policies. In language model, if you get the language model to fail, you go into Twitter and announce that, look, I managed to confuse it, and you even write papers about it. So for robot policies, when you get it right is when you go to Twitter, right? Most of the times they fail, simply because we're early still in the research on the field. Like, I'm pretty sure after 5 years, it's not going to be the same situation, but right now this is where we are. So I just want to say that I personally believe a lot on this. We like this behavior benchmark. We have released recently a simulator called the Genesis physics engine, and we have put effort on trying to procedurally generate, not only procedurally, but also use generative models to generate meshes and textures and scenes and tasks and rewards by looking at generative models, okay, and asking language models to design tasks, much like what you hinted earlier, how can we procedurally scale up such task development, okay? And, but the truth is that this would just accelerate what behavior did. So again, we're going to end up with a benchmark that nobody would like to use because they're going to get very low numbers. So what we said is the following. What if we bring the benchmark in the frontier of whatever robot policies can do today? What if we start from their training data? And this is a video, this is a demonstration video from kinesthetic, essentially, demonstration where you have the RGB sequence and the body joint sequence of the robot. This is part of this open embodiment data set that many foundation models are trained on with behavior cloning. And what if we take that video and we make a simulated scene out of that, and then we start perturbing that scene, and we evaluate the robot policies automatically in these perturbations, okay? So we are very excited about, pushing, this Genesis dream of, procedurally generated tasks, etc., just by asking language models to imagine the scene, etc., but me being a computer vision person, a supernatural thing to do is just look at the video and just make a corresponding simulated scene, which then you can perturb and essentially test generalization and really stress test the abilities of those policies in a scalable manner. And this is what we did. We took lots of videos from what policies were trained on, and we converted them into simulation environments automatically without any human involvement. And we made this benchmark we called RobotArena. We say unlimited robot evaluation via demonstration to simulation translation. And we call this unlimited because the real to sim translation is, doesn't use a human in the loop. Now, this was a very difficult project, and it still is, and I'll show you the current limitations. And the reason it's a challenging project is that this real to sim is not a code that you can download from the internet. In fact, it is the computer vision problem that, it has made tremendous progress the last few years, and this is where this RobotArena is based on, but it continuously changes from month to month, okay? And this is a pipeline that's completely going to be updated from month to month. So RobotArena is based on this real to sim translation, as I said, that has multiple steps that I will go through, from calibration to object detection, reconstruction, background fixing, placement of the assets, system identification, and the automated evaluation. Because once you make the scene and you define the task, you also need to automatically evaluate, the policy acting in that environment. So the first problem we had, once you have a video and the robot is acting in that video, is you need to decide, like, which robot it is. Let's say it's Franca. So you take the URDF of Franca, put in your simulator, then you need to decide where to place the camera, okay? And this is the notorious problem of camera calibration, robot camera calibration, which, you would expect that's going to be ready and solved. But one of the biggest problems of demonstration data sets is that, they have annotated body joints, but they don't have annotated task space trajectories, because calibration is just so brittle. And, you calibrate, then somebody pushes the camera and so on, or the robot moves and things move and so on. So the first thing we spend a lot of time on is to try to automate this process. And the way we do it is we take this nice paper from Coral 24, which is actually has a very simple idea. It's a translation from body joints of the robot. What you see there, the P vector, this fed into a neural net. And this neural net spits out 3D Gaussians, okay? 3D Gaussians, which is a 3D differentiable representation of the scene. And the way you train that neural network is by rendering those Gaussians differentiably into images, putting losses on those images, like make sure you replicate how the robot looks from different viewpoints. And you essentially create data in simulation by varying the body joints and by varying the camera viewpoints. And that's how you train this mapping. So now for Franka robot, you need to repeat this for every robot morphology, by the way. But for each robot now, once you train that, I'll give you the body joints, and you'll be able to show me how the robot will look in the 3D world, all right? And next, once you do that, and the interesting thing is that we're using demonstration datasets where body joints at every time step are annotated. This is exactly what foundation policies use, right? They use image to body joint angles mapping. So once you train that, what you do next is you learn that rotation and translation. You freeze now that doctor robot neural network, and you learn the rotation and translation of the camera with respect to the robot, okay? And as you vary, essentially you search over camera placements. Each time you render your 3D Gaussians and match against the bottom-up image. And the result is you start from a very noisy calibration where, you know, the robot really doesn't fall on top of where it's supposed to be. And during this optimization, essentially test time optimization, where you backpropagate directly to this transformation, you figure out the right calibration. So then once you have that, now you know how to place the camera. The next thing is you need to detect the relevant objects of the task. And we do this using Gemini 2.5. This came out like 1 month before the submission, and it had dramatically better results than the previous version of Gemini. Okay, so that was a big help, because now we can automatically segment the relevant objects on the scene in the image, as well as label them, like red tomato and metal pot. Now, once you do the segmentation, there are incredible models that I'm actually extremely excited about from many startups in Asia. One of them is Hongwan 3D. And again, there is 2.0 came out, 2.5 just came out, even better, and so on, that will take your object crops and make 3D meshes for you in a feed-forward pass, very fast. And then these are just geometry. The next you need to prompt the VLM to give you some physics properties for those objects. So this is what we do. And once you have the physics, then you put them inside the simulation. All right, and now here is now the interesting thing. So far, we haven't made a 3D mesh of the background, but this is what we're working on. But right now, what we're doing is we take this image and we complete the holes, and it's like a poster that you put on the background of your simulator. All right, so that the policies can be fooled that this is, let's say, a real thing. Now. Yeah, so I'll tell you the extensions of that. But for now, let's assume there is this poster. Now, we have our objects in 3D. Unfortunately, when they're reconstructed from image to mesh, they don't have the right orientation. So you need to estimate that orientation. You need to rotate them the right way that is in the image. And then you superimpose them. And here is like the corresponding simulation that you get. The camera is placed correctly, and the objects are there, and they have physics. And this all happens in the Genesis physics engine. And here is some examples of this. So now you deploy the policies, all right? And that's what they do. They pick up the object, they put in the right place, and so on. Now, one more thing we did, we had to search for the right PD robot gains. How did we do that? Well, we have one trajectory in the real world, we run with the same actions, the same trajectory in the simulation, and we search for these two parameters so that these trajectories exactly fall on top of one another. So you also need to do that, like a very basic system identification specifically for the robot controller. Now that's it. Now the next important part, again, we were stuck, is how do we automatically evaluate those policies? Our idea was, no problem, we're just going to go to Amazon Mechanical Turk. And in fact, we wanted to do exactly the same thing with LM-Arena, and actually we're doing it. For the same task, we let two VLAs act. We get the videos, we show it to the human, and the human casts a preference. So we think this is important to have actual human preferences, because maybe both robots succeed, but one robot succeeds faster, or one robot is more graceful, or one robot is less scary. Humans have so many preferences of how they want the robot to execute things, which right now we're not thinking about because our robots are incompetent. But once they become competent, all these things matter. For example, for Waymo, it very much matters if the human doesn't feel threatened, or the human doesn't feel that this is going too slow, and so on. So you need to find the right balance for what the humans like. But here is now an automated way to do it. We take the video of the task, and we shuffle the video frames, and then we feed it into Gemini and say, give me task progress scores. And because you shuffle the frames, Gemini will not memorize to give you 0, 10%, 20, 30, 60, 80, but will give you a reasonable, somehow, task progress. You tell him, I'm going to show you now a video of this task. You tell me how you think the task progress is going. And this is a very recent paper, ICLR 2025. So these things are possible only now. If you try the previous versions of Gemini, we measured correlation with human preferences, and these correlations are much worse. Okay, this was much worse before. So now we have an automated way to evaluate our videos. And here is the four policies that we considered, foundational VLAs: CogAct, RoboVLM, Spatial VLA, and Octo. So we took those VLAs and then we deployed them on our simulated arenas. But instead of just deploying them on the original environment, we also did a lot of perturbation. So we changed the color, we changed the background. So here's how the background looks different and the color looks different. And we move the camera placement, and then we also move the way the relevant objects are positioned in the scene. And then we score them, and we see, interestingly enough, that, under a lot of evaluations, CogAct actually is pretty much the best VLA out of the four. Then is RoboVLM, and then it's Spatial VLA, and then it's Octo. And now you may say, why didn't you also use Pi 0 here and Pi 0.5 and so on? And the reason is that those models use wrist cameras, and a big limitation of our benchmark right now is that you can only have a head camera. However, this is changing right now because there are generative models that seated on a single image, it can generate, and a camera path trajectory, they can generate images. And not only they can generate images, but they can do this in a very geometrically accurate way by essentially feeding 3D Gaussians, which they render, and they use as a conditioning scheme for generating the rest of the images. And this actually was a paper we found in CVPR 2025. We were trying to implement this ourselves, but now we have it ready. So my point is that generative models do, very recent progress in generative models does give us ways to really push this real to sim automation. Yeah, so, and I want to mention here a work here that Carl may discuss when he comes later today in the workshop. We were inspired by this work, Simpler, but the problem with Simpler is that it has only 3 simulation environments with 2 tasks. They also try to do this real to sim translation with a human in the loop. So a human needs to go and place the camera, they need to decide where to place the assets, and so on and so forth. And we also found that if you a little bit move the assets, there is dramatic failure in performance, which is not a general trend in our environments. So we thought that if we really want to scale that benchmark, we really need to automate that real to sim translation as well as the evaluation. So they have hard-coded reward functions. What we're working on right now, we're working on really scaling up the number of arenas. We have about 150 environments on Bridge and 50 in Droid benchmark and in RH20T and RoboMind. We're trying to essentially take a lot of videos from those data sets and move them into simulation. There are some tasks that cannot be simulated easily. For example, if you plug, let's say, a charger into a socket, the simulation is not ready for that. We are excited about Genesis because it can simulate cloth and water, much slower, but here we don't care to do RL, so it's okay. So it can handle more tasks than other, let's say, physics engines. And this is basically what we want. I just discussed now the limitations, essentially. So the takeaways is that simulation should be a big part of the story of benchmarking robot policies. We don't think that it should be the only one, but it should be a big one because it can give feedback to the developers of how their models are performing. And the idea of our benchmark is, let's start close to the training data. There's no reason to do that. As robot models become more and more competent, you can just come up with new tasks in simulation without trying to do demonstration video to simulation translation. Yeah, where we're going, well, we want to put now, we're super inspired with the recent work on humanoids and mobile manipulation. So all these tasks we want to be able to add in our simulator in a scalable manner without needing, an army of, graduate and undergraduate students feeding simulation environments to us. And with this, thank you very much, and I'm happy to take your questions.
Questions? How do we establish trust in this pipeline as being a useful surrogate? Like, how do we trust that the generative models, meshes, everything somehow is telling us about performance in the real world?
Yeah, this is a very good question. So first of all, we can do it explicitly. We can, take some trustworthy people and ask them to do the real world evaluations, which I showed you in the beginning how painful they are, and then check the ranking of the policies in the real world in comparison to the simulation. Okay, another thing we can do is we can feed motion planners, like we can assume Oracle privileged information in the simulation and get motion planners and say, look, a motion planner can achieve the task. All right, you say, okay, here is the grass pose, here is I know exactly where the object is, I know the grass pose, I go there, I know the end location, I put it, and then I have a proof that, look, the task is actually solvable. Now, it might be that this tomato is a bit heavier than, most of real world tomatoes. It might be possible, but, if your policy is indeed general, it should be able to handle that variation over the real world that actually I'm showing you in the simulation. So there are ways to create proofs to say, look, I was able to solve it with privileged information, just solve it now with pixel input. But this is a great question.
I have a quick question. So the sort of paradigm of doing real to sim in this case, like when you're modeling things like dynamics and contact, you still at some point have to use a traditional simulator. So I'm wondering, are there aspects of robustness that we can't properly evaluate here, or we can't sort of move the needle on evaluating, like evaluating different highly dexterous tasks with very complex contact dynamics?
Yeah, we are using an traditional physics simulator here, right? But you're saying physics engines just cannot do real contact-rich tasks. Yeah, I think that is possible. This is possible. Let me think a little bit. Well, the truth is the following. In this conference, we did see a lot of large-scale RL for tasks that are reasonably dexterous. For example, any grasp to any grasp. Reposition the object in your hand. Okay? I mean, this is kind of an easy thing because you just have a rigid object and you just replace it in your hand. I think this thing that I just said earlier, like this socket or putting the charger on your laptop, I mean, yeah, with traditional physics engines, there's no way this is going to be accomplished. Now, my big dream is that physics engines are part of the research problem. The same way we are making VLAs better and better, the physics engines and simulators also need to be getting better and better. And maybe we can do a little bit more hybrid simulation where things are very hard to simulate with explicit Newton equations. Maybe you can put some learning-based, transition dynamics and patch them up or something. So I do believe that physics engines also will keep getting better. About specifically the assets, I just want to mention the incredible, unfortunately it's only that group in NVIDIA that does that, but this incredible work from Factory and Matchmaker, they make really incredible assets for drilling and screwing and bolts and so on, and that work absolutely amazingly well. The Matchmaker shows how to do really assets that really lock in an automated way. So I believe what is now an outlier, a research outlier from only this group, potentially is going to spread, and we'll be able to have much, much better assets, even for this type of task where, you really need to match to like a weapon.
Yeah, quick.
I may have missed it in the segmentation section, but where do you get the workspace? It's a table or
Yeah, very good. So we are working into full meshing of the background scene, and it is totally possible with current technology. We believe this is totally possible. Right now, we just have a flat surface, and we put a poster. We don't put a poster. We render this background to full the policy that, oh yeah, this beautiful stove, despite the fact that there is not an explicit stove there. This also should change pretty soon, though. Yeah.
All right, well, thank our speaker.
Thank you very much.